In this lecture, we'll look at an application of max flow to a problem from computer vision, known as image segmentation. We're given an image such as this one, and our goal is to separate the image into objects. The easier task that we're going to look at is to simply separate the image into foreground and background. For example, in this image, we want to discern the triangle from the rest of the image. We're going to view the image as lying on a graph, where the vertices of the graph correspond to the pixels of the image. So let's look at an example of a pixelated image. Here's an example of a small pixelated image magnified. The input is going to be specified by an undirected graph, G. The vertices of the graph once again correspond to the pixels of the image. So there are 9 vertices in this example. And the edges will go between neighboring pixels. The input once again is specified by an undirected graph, G, where the vertices correspond to the pixels. And in addition, we have the following parameters. For each pixel, we have 2 parameters, Fi and Bi. Fi is the likelihood or weight that vertex I, pixel I, is in the foreground, and Bi is the weight or likelihood that pixel I is in the background. Now we'll assume that both of these parameters are non-negative. In addition, we're given a parameter for each pair of neighboring pixels. Pij is the separation penalty for this edge. It's the cost of separating I and j into different objects. And once again, we'll assume that Pij is non-negative. Here's our example of an image from before. Let's look at an example setting of the parameters in this case. Here are example settings for the foreground and background likelihood for this image. So we're saying that the white pixels are more likely to be in the foreground, and the black pixels are more likely to be in the background. For this image, we could have just as well reversed what we call foreground and background, since we've defined the matrix to be symmetric. And here are sample separation penalties. And when the pixels are different, we don't pay any penalty for separating the pixels into different objects. Now keep in mind, this is very much a toy example. All the pixels are monochromatic. So we've chosen very simple weights in this example. Our goal is to partition the vertices or pixels into 2 sets, F and B. F will correspond to the foreground pixels, and capital B will be the pixels that we assign to the background. Now for a particular partition, FB, we need some score or weight to measure the likelihood of this partition. Thus we define the weight of this partition as the following. For each pixel assigned to the foreground, we get Fi. For each pixel assigned to the background, we get Bj. I've used different indices for these 2 sets to avoid some confusion. Finally, we pay a separation penalty for separated edges. This is a penalty, so we're going to subtract it. And we're going to look at all edges where the first endpoint is in F and the other endpoint is in B, or vice versa. And the penalty is, of course, Pij. This defines the weight for a particular partition FB. So for a particular assignment of the pixels to foreground and background, we have a weight associated with it. Our goal is to find the partition or assignment of pixels to foreground and background with maximum weight. Now our goal is to reduce this problem, this maximization problem, to the min-st cut problem. So we have to somehow change this maximization problem into a minimization problem. So we're going to have to modify these weights. And the other issue is that we're summing some terms and we're subtracting other terms. Now all of these parameters are non-negative. In our min-st cut problem, all of the capacities in the input flow network are all positive. So we somehow need to change this minus of the separation penalty into an addition so that all the terms are positive or non-negative. Look at the sum of all the foreground and background likelihoods. So let capital L denote the sum over all pixels of their foreground likelihood plus their background likelihood. Recall our weight for a particular partition FB had weight Fi for each pixel assigned to the foreground and Bj for each pixel assigned to the background. Notice that this quantity is equal to capital L minus the sum of the pixels assigned to the foreground of their background minus the sum over the pixels assigned to the background of their foreground. Because if we take the sum over the pixels assigned to the foreground of their foreground likelihood plus the sum over the pixels assigned to the background of their foreground likelihood, we get the total likelihood of all pixels for the foreground. This is the first term in this sum. Similarly, by summing this term with this term, we get this total likelihood of all pixels for the background. Now if we subtract the separation penalty for separated edges, now I'm thinking of this ij as an unordered pair, so I don't have to write both cases. I and F or J and B. If this is an unordered pair, that covers the other case where I is in B and J is in F. Now to maintain equality, I want to subtract this term also from the other side. Now what do you notice about this left-hand side? Well, this is exactly our definition of the weight W of FB. Now we're going to define a new weight W prime of FB, which is the sum of these three terms. And then the right-hand side will be equal to L, capital L, minus W prime of FB. Now just to summarize, we let capital L be the sum of the foreground and background likelihoods for all pixels. Now for a partition FB, we defined its weight to be the following quantity. It's the sum over the vertices assigned to the foreground of their foreground likelihood, plus the pixels assigned to the background of their background likelihood, minus the separation penalty for separated edges. Now let's define a new weight, W prime. This is the sum over vertices assigned to the foreground of their background likelihood, plus the sum over vertices assigned to the background of their foreground likelihood. And now we'll add, instead of subtract, the separation penalty. And the key point is that these two quantities are related in the following manner. W of FB equals capital L minus W prime of FB. The separation penalties cancel from both sides, and then when you add up these remaining terms, you get capital L. Now the point is that if we find the partition FB which maximizes the weight W of FB, this is equivalent to finding the partition FB which minimizes W prime. Since we're subtracting off W prime, minimizing this term is the same as maximizing the whole quantity. So we've changed our maximization problem into a minimization problem, and all of the terms in W prime are positive. So now this is in potential form that we can convert it to a min-ST cut problem. And how do we solve the min-ST cut problem? We solve it by doing the max flow problem. So we're going to define a flow network, solve the max flow on that flow network, and then that'll give us the min-ST cut solution. Here's our new problem formulation. The input is an undirected graph corresponding to the image once again, and we're given the following weights. For each pixel, for each vertex I, we're given Fi and Bi, and these are non-negative weights. And for each edge, we're given the weight Pij, which is also non-negative. And our goal is to find the partition of the vertices or pixels into two sets, F and B, and we want the partition which minimizes the weight W prime of FB. Recall the partition FB which minimizes W prime of FB is the same partition which maximizes W of FB, and therefore it solves the original image segmentation problem. Now let's see how to reduce this to the max flow problem. Now to convert this new image segmentation problem into a max flow problem, we have to define the flow network, which is the input to our max flow problem. Now the input to the image segmentation problem is an undirected graph. Now a flow network is a directed graph, so we have to take this undirected graph and define a directed graph G prime. Now here's our example input to the image segmentation problem. This corresponds to a natural undirected graph. What is the corresponding directed graph? Well, here are the vertices of this graph, and instead of putting undirected edges between neighboring pixels, we'll put bidirectional edges. So these bidirectional arrows denote edges going from this pixel to this pixel and vice versa, this pixel back to this pixel. So this is a directed graph corresponding to our undirected image. So for each edge in our undirected graph, we add an edge from I to j and j to I. Now what are the capacities on these edges? Well, we want to keep track of the separation penalties, so it's natural to put capacities which are the separation penalties. So both of these edges will get capacity Pij. Now that encodes the separation penalties. What do we do with the foreground and background likelihoods? Well, we're going to add additional vertex corresponding to the foreground and an additional vertex corresponding to the background. So we're going to add a vertex S, a source vertex, corresponding to the foreground pixels. Now here's the same directed graph once again with the vertices shrunk a little bit just for illustrative purposes. Now we're going to add two additional vertices, S and T. S will correspond to the foreground, T will correspond to the background. And this will be our source and our sink for our max flow problem. We're going to add an edge from S to every pixel, every vertex. So for every pixel in the original undirected graph, we add an edge from S to I. Now S is supposed to correspond to the foreground, so the capacity of this edge will be Fi, so we encode the foreground likelihoods. Now for the background we do similar, using this vertex T. So we add an edge from every vertex of the original undirected graph to T. So these edges are going to T, whereas edges came out of S. So S was a source and T is a sink. And the capacity of these edges to T will be the background likelihood. So now we've got the foreground likelihood and the background likelihood encoded. And we have the separation penalties encoded. So here's our final graph. And we've specified the capacities along every edge. Therefore, we've defined a flow network, and we can use this as our input to the max flow problem. Now we're going to take this flow network and we're going to run the max flow on it. We're going to get a flow of maximum size, and we know that the size of the maximum flow equals the capacity of the minimum ST cut. Now let's try to understand ST cuts. For a particular partition FB, what is the capacity of that cut? Recall the capacity of this cut are the capacity of the edges that go from F to B. So which edges go from F to B? Recall we only get these edges that go from F to B. We don't get the edges that go from B to F. So let's define a partition, a cut in this graph. Let's suppose that these 4 pixels get assigned to the foreground. So this is our set F, and the remaining 6 vertices are in the background, B. Now which edges cross from F to B? Now consider one of these 4 pixels in the foreground. Notice its edge to T crosses this cut. So we get this edge from I to T, and what's the capacity of this edge? It's BI. That was our definition of this flow network. Similarly, look at these pixels assigned to the background. For each of these 5 pixels, we get the edge from S to that pixel. And that edge from S originates in F and ends in B. So it crosses this cut from F to B. And what's the capacity of this edge from S to this pixel? And that was defined to be Fj. Finally, for each of these separated edges, we get the edge in one direction, but not the other direction. We get this edge, this edge, this edge, and this edge. But notice we don't get the other direction edge. So for each edge in the original undirected graph, if I is assigned to the foreground and J is assigned to the background, then we get the edge from I to J, and the capacity is Pij. Now if you sum up these terms, what do you get? That's the capacity of this cut, FB, and that's exactly equal to W prime of FB. That was our definition of W prime. We summed over pixels in the foreground of BI, pixels in the background of Fj, and the separation penalty. That's great. Our capacity is exactly equal to the quantity W prime, and our goal was to minimize W prime. If we run max flow, we find a min ST cut. That's a cut with minimum capacity. So we found the cut, the partition, which minimizes W prime. So we can summarize our solution to the image segmentation problem. Given our original input to the image segmentation problem, this consists of an undirected graph corresponding to the image, the foreground likelihoods, background likelihoods, and the separation penalties. Then we define our flow network. This consists of a directed graph. We take this undirected graph, make each edge bidirectional, and then we add S, which directs to every vertex in the original undirected graph, and we add vertex T, which has an edge from every pixel in the original undirected graph to T. That defines the directed graph, and then we define our capacities. Then we run max flow on this flow network, and we get a flow F star of maximum size. Now the size of this max flow equals the capacity of the min ST cut. This is the max flow min cut theorem. And in fact, we can take this max flow and construct a cut of minimum capacity. And we just saw that the capacity of a particular ST cut equals the weight W prime of FB. Therefore, by finding the cut of minimum capacity, it's equivalent to finding the partition of minimum weight W prime. Now, our original problem was to find the partition of maximum weight W. Well, this is the same as capital L, this normalizing factor, minus the min over partitions of W prime. So if we find the partition which minimizes W prime, that's the same partition which maximizes W. And therefore, we've shown how to solve the original image segmentation problem using the max flow problem.